Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for those who are going through Calc 2 and are just learning about improper integrals. This topic I usually treat in class, and I go through pretty detailed examples. However, there are often some really oblique examples, some oddball examples that you don't get time for in a class that I would love to approach at some point, and what better time than now when I have the ability to go ahead and make a video recording. So just to let you know, if you're not one of my students, the idea that I teach my students when you have an improper integral is to first of all use your intuition. Do you think this improper integral converges or diverges? This all pretty much centers around one basic theorem. And that is the improper integral from a to infinity of 1 over x to the power p dx. Well, that integral will converge if the power p is strictly greater than 1. It will diverge otherwise. Now, this actually doesn't help in every situation, but it gives you an intuition as to what causes the convergence of an improper integral or the divergence. Generally speaking, if you can write it as a constant over a polynomial, and the degree of that polynomial in the denominator is greater than 1, then you know it's likely to converge. That's the intuition. Of course, you will have to prove that. Well, in our first case right here, notice the denominator has more than just a polynomial. It has a polynomial x, and then it has an exponential e to the negative x. However, if you use a little bit of intuition here and think about the numbers that you're integrating from and to, well, if you're integrating from a lower limit of 7 to an upper limit that's approaching infinity, that e to the negative x is essentially getting smaller and smaller, a very, very small number. E to the negative 7th is 1 over e to the 7th. It's an incredibly small number. And then as time goes on, as our inputs approach infinity, well, e to the negative x will approach 0. So that tends to be inconsequential in the end. Intuition-wise, that makes sense that this will disappear, and we're actually looking at the integral of 1 over x. However, that's not a proof that we're looking at the integral of roughly 1 over x. But if we were looking at the integral of just 1 over x, then the power would be 1, and therefore we would know, because the power is less than or equal to 1, that the improper integral should diverge. So that's our intuition. We're using a little bit of intuitiveness here to go ahead and make a claim. I think this diverges. That will inform us of how we're going to set up our comparison. And I'll even write that down actually. So by intuition, I'm saying it's likely going to diverge, but now we need to prove that. And the only way we can prove that is to get it to somehow be a 1 over x. And what I tell my students to do is to look at the denominator first and create some type of bound for that denominator, and then take the reciprocal and whatnot. It's just a little bit easier, I think, to do that. So here's what I'll do. A little bit of scratch work is very healthy. So we have our denominator is x minus something. And by the way, exponential functions, e to the negative x, those are always positive. So this is x minus a positive number. If that's the case, that's always less than x. Now, I don't know if that's going to help us, but at least I know that that is a truth. X minus e to the negative x is always less than x. If you take the reciprocal of both sides, this will imply that 1 over x minus e to the negative x, well, that is going to be greater than 1 over x. And by the way, 1 over x is greater than or equal to 0. Technically, it's strictly greater than 0, but I'm writing greater than or equal to just because the theorem that we use for the comparison test has that, but you don't actually need it. So I'll go ahead and compare our integral to the integral from 7 to infinity of 1 over x. And we know that the integral of 1 over x from 7 to infinity, that diverges. It diverges actually by the power test for integrals. But now that we stated that, well, if the area underneath this curve grows to be infinite or diverges, and you have another curve that's greater than that, well then the curve that's greater has to also diverge. And therefore, the integral from 7 to infinity of 1 over x minus e to the negative x dx diverges, and that will be by the integral comparison test. And from this point forward in this video, I'm going to just abbreviate that to be the ICT. So this first example is not too terrible. It's just a really kind of starter example so you can get an idea of how I teach my students to showcase whether an improper integral is convergent or divergent. Now let's move to a second example. Each of these examples is meant to grow in complexity. Now with this example, there are two ways to approach it. If I'm going to, first of all, think about my intuition here, intuitively, I might say, oh, this will diverge because it's like a 1 over x, but it's not like a 1 over x because as x tends to infinity, this will tend to negative infinity, and therefore e to the negative x will tend to 0 very quickly, in fact. And so therefore, because this is being sucked down to 0 very quickly, the area underneath this curve is likely to become something close to 0 very fast. So my intuition is saying that this is likely actually going to converge because, again, the area underneath this curve not only tends to 0, but it's going to do it very quickly. And that very quickly sentence, or statement, I guess, is the important factor here. 1 over x, in fact, tends to 0. We know that. However, the integral, or the area underneath 1 over x, will diverge. It'll become infinite. So that doesn't go to 0 fast enough. But 1 over e to the x, that definitely goes to 0 fast enough, in my opinion, for it to allow convergence. So my intuition here is that this is going to converge. And remember, when you want to show that something converges, if you want to show that this integral specifically converges, you need an upper bound, a function above it that you know converges. Well, let's look at these two functions within this integrand. It's an e to the negative x and an x. Or better yet, it's an e to the negative x and it's a 1 over x. Well, comparing to 1 over x is going to be a very bad idea because that's not going to go along with what I think is going to happen. I think this will converge, and comparing to the integral of 1 over x, well, the integral of 1 over x diverges. So that's not going to be the best one to go with. A little bit of rewriting of the integrand will allow us to see what might be a better choice to compare to. In this case, I see in that denominator really what's the biggest bully on the block. The function that's taking over in the long run is the e to the x, and I can integrate a 1 over e to the x. That's just integrating e to the negative x. So I might want to just compare this to e raised to the x power, or 1 over that. Again, when you look at my fraction 1 over e to the x versus the fraction we're actually dealing with, which is 1 over x e to the x, you have to start thinking about how are you going to make an inequality between these two fractions. And as I advise my students, it's often, maybe not always, but often a very good idea to just look at those denominators. Look at x e to the x and compare that to e to the x. Well, remember what x is starting at. It's starting at 1 and going to infinity. And we'll have a little note on the interval over which we integrate in a little bit, because it turns out that we can kind of throw out early iterations here. So if this started at a value that was not going to help my argument, I might want to bump it up. We'll talk about that briefly in a moment or in a couple of examples. But for right now, as long as x is between 1 and infinity, then x e to the x must be greater than e to the x. Again, x is greater than or equal to 1. So you're basically throwing on a coefficient on e to the x that's greater than or equal to 1. So therefore, x e to the x is actually greater than or equal to e to the x. That being said, Now I'm going to make the fractions by taking the reciprocal of both sides. And you can see the function that I really think when I integrate, I can showcase that converges is above the function I want to show convergence for. By the way, this is greater than or equal to 0. And you'll have to forgive my language too, because I'll say things like the function we want to show converges with it, when in reality, I truly mean to say the function whose integral converges. I just have a habit of really messing up those words. So let's go ahead and investigate the integral of 1 over e to the x, which is the same thing as the integral, and again, we're going from 1 to infinity, of e to the negative x. Remember, an improper integral is a limit, and you're not allowed to not write the limit notation. You have to write that limit notation when working with improper integrals. Let's go ahead and find the antiderivative here. And now let's factor out that negative, and I'll do that over here. Once we have evaluated the integral, we can now evaluate the limit. And we know from calculus 1 that as n goes to infinity, e to the negative nth will tend to 0. Thus, this limit will turn into a negative, or in other words, a positive, which I'm not going to write the plus there, e to the negative first. I don't really care about its value other than that it's finite. That's all I really care about. So I happen to know the area under e to the negative x, which is the area underneath 1 over e to the x, from 1 to infinity, is finite. And because that area is greater than the area underneath this curve right here, I know the area of 1 over x e to the x must therefore be finite as well. So since, again, I'm just repeating myself, but since the integral from 1 to infinity of 1 over e to the x dx is convergent, and because 0 is less than or equal to 1 over x times e to the x, which is less than or equal to 1 over e to the x, well, that integral from 1 to infinity of 1 over x e to the x must converge by the integral comparison test. Again, a couple basic examples. Now let's move into a less basic example. It's still not too terrible, but it's still important enough to talk about. The integral from 1 to infinity of e to the negative x squared. And sorry, my ink is a little bit wild today, so let me clean that up. Now, if you think about that, intuitively, we should know that will converge because that's the same thing as the integral from 1 to infinity of 1 over e to the x squared dx. And that will tend to 0, the integrand that is, will tend to 0 so quickly that it just seems obvious that this area underneath this curve will be finite. It will converge, the integral will. But the one thing you want to do here is you want to somehow prove that this converges. And to integrate this is terrible because this is a non-elementary function, e to the negative x squared. You cannot actually integrate by hand. It just can't be done. So we need to compare it to something that we actually can integrate that also converges. Again, we're saying this converges. So we want to compare it to another integral that is improper that also converges. Well, how are we going to do that? We just proven actually that 1 over e to the x from 1 to infinity converges. That's right over here. The integral from 1 to infinity of 1 over e to the x, which is just this guy right here, we've proven that that converges. So it might be nice to use that. So let's compare 1 over e to the x squared to 1 over e to the x. And to do so is going to require some justifications. The first thing you need to do is set up an inequality that compares 1 over e to the x squared to 1 over e to the x. And that is somewhat challenging. If you think about just the denominators, e to the x squared versus e to the x, you need to argue one is greater than the other. Well, in this case, it's somewhat obvious which one is going to be greater than the other as long as x is greater than 1. Technically greater than or equal to 1. Probably a good way to see this is to compare x squared to x itself. So as an aside, off to the right-hand side, I want to showcase something that you should have learned in your Calc 1 course, but often it gets kind of brushed aside, or that the instructors are just not spending, well, it's not that the instructors are not spending time on it. It's just that it's a minor part of Calc 1 that can be swept under the rug and you forget about. But this, we're going to use something called the racetrack principle. I want to look at x squared versus x. Now, the racetrack principle is actually the result, or a result, of the mean value theorem. The racetrack principle says the following. If you have a function evaluated at an initial time a, and that's greater than or equal to a different function g evaluated at the same initial time a, and if you happen to know that the derivative of your first function is greater than or equal to the derivative of your second function for all x greater than or equal to a, then the first function is greater than or equal to the second function for all x greater than or equal to a. Now, that sounds confusing, but the name of this theorem, which is the racetrack principle, is incredibly powerful and easy to understand if you think of it in terms of a racetrack. So, without abusing a horse in this race, let's just talk about mathematical horses. So let's suppose that you have a race and it starts at x equals 0. Or actually, let's just keep it arbitrary, x equals a. And at time a, the horse, F, is at this position. But at the same time, the horse G is also at that same position. So these horses start neck and neck, or head to head, or whatever you want to call it. They're at the same position initially. And then they say, go. Well, if F is always faster, that's why it's F. If F is always the faster horse, that means that when you start graphing the function F, it'll rise faster than the function G. So again, if the horses start at the same point, or if the faster horse starts with a head start, and if the faster horse, well, if the faster horse is a faster horse, that is, its speed is greater than or equal to speed of G, for all x greater than where they started, then over the long haul, that green horse, the F horse, the faster horse, is always going to be ahead of the blue horse, G. And that should make sense. So how does this apply to this problem right here? Well, I'm going to claim that x squared is greater than or equal to x for all x greater than 1. Go ahead and call this horse F and this horse G. F at time 1 is 1, and guess what? G at time 1 is also 1. So these horses are neck and neck right at the beginning. However, F prime of x is 2x and G prime of x is 1. And for x greater than or equal to 1, 2x is going to be greater than or equal to 1. You're plugging in numbers 1 or greater. So that makes sense. I'm using somewhat of a trivial example here, so you could prove that using the racetrack principle if you want to, but I'm just going to make the claim right now that F prime is faster than G, or sorry, F is faster than G, because F prime is 2x, G prime is 1, and for x greater than or equal to 1, F prime therefore must be greater than or equal to G prime. So to reiterate, we have two horses. They start at the same place, but one horse is always faster than the other horse. And because of that, the first horse, F, is always going to be greater than or equal to the second horse, G, for all x greater than or equal to 1. That is, F was x squared, G was x, so therefore x squared must be greater than or equal to x for all x greater than or equal to 1. You can use that same argument to showcase that e to the x squared is greater than or equal to e to the x. However, I'm not really going to go through that entire argument. I've just shown that x squared is greater than or equal to x. Therefore, when you raise both sides base e, since x is greater than or equal to 1, e to the x squared must be greater than or equal to e to the x. Don't lose sight on what you're trying to prove. You're trying to prove that this improper integral converges by showcasing 1 over e to the x is greater than 1 over e to the x squared. Well, we have e to the x squared and e to the x right here. Let's take the reciprocal of both sides. There's the inequality we wanted. And by the way, this fraction is always greater than or equal to 0, which is important for the comparison theorem. And now we know from our previous problem, the integral, we're starting at 1, so that's good. The integral from 1 to infinity of 1 over e to the x dx converges by the previous problem. And therefore the integral from 1 to infinity of 1 over x e to the x dx converges by the integral comparison test. Now just a little heads up here. If let's just pretend that this integral was not going from 1 to infinity, but instead was going from, let's pretend, 1/2 to infinity, or something like that, or 1/10, doesn't really matter. So how would that change the problem if it was going from, again, like a 1/2 or a 1/10 or whatever to infinity? I would still like to compare it to the integral from 1 to infinity of e to the x, of 1 over e to the x, sorry. And the reason why is because I know that this integral splits into a proper definite integral and an improper integral. And I happen to know this area right here because there's no domain issues over the region 1/2 to 1 for the function in question. That's just a finite number. I don't even care what the number is. I just know that's finite. And so if I have finite plus a convergent improper integral, it's going to be finite plus finite, which is still finite. So this is another thing you need to be aware of when you deal with improper integrals, is that every once in a while, they give you an interval of integration that you might have to adjust a little bit. Just throw out the pieces that are finite because those don't affect the convergence or divergence of the entire improper integral. In fact, the convergence or divergence of this improper integral right here, I could actually do that entire problem based upon throwing out everything from 1/2 all the way up to 100 and integrating from 100 to infinity of 1 over e to the x squared dx. Because again, the area from 1/2 to 100 underneath that curve is just some finite number. If I want to throw it out, I'm allowed to, because the finitude of that number will not affect the convergence or divergence of the rest of the integral. So I hope that makes sense, but we're going to do one final problem here. And this final problem was actually the progenitor or the reason why I made this video. One of my students contacted me and said, whoa, hey, hold on a second. I tried to do this problem and it's not working. It's not working with the method that you taught. They didn't say it that way. They were very nice about it. So let's talk about this. And I couldn't stand it. I had to clean up my ink there a little bit. Now, if you adhere to what I've been teaching in class, something goes wrong here. Not by my intention, just by chance. The first thing I'm going to do here is I'm going to make a claim about what I think will happen. If you take a look at this integrand, it's roughly a 1 over x to the 6/7. It's not exactly that, but it's roughly that. And because that power there is less than or equal to 1, my knowledge is that the area underneath that curve from wherever to infinity will be infinite. The improper integral of 1 over x to the 6/7 will diverge. So I'm going to write down my intuition. I think this integral is divergent. In fact, I know it is. So we need to compare it to a fraction. Sorry, we need to compare the integrand to a fraction that is less than that integrand. Because if you compare it to a fraction less than that integrand, and the integral of that fraction that is less than your integrand here ends up being divergent, then that'll push this to be divergent as well. As I say in my class, convergence above forces convergence below. Divergence below forces divergence above. So I need something below this. Well, it seems pretty obvious, at least at first glance, that we would like to compare this to 1 over x to the 6/7, because, well, guess what? That diverges, right? So I'm going to start by writing that down. I'm going to write it in red because, to be honest with you, it's not going to work out. We happen to know that that integral, that improper integral, will diverge just by the power test for improper integrals. So we'll have to start creating an inequality comparing those integrands. Well, I'll start with just x. I think it's pretty okay. I think most people watching this video would agree x is equal to x. And that will imply, let's see, where do I need to go with this? I need a sixth power on this x. So let me go ahead and raise both sides to the sixth power. And again, I think most people would agree with this, right? However, looking at what this black ink says, we need to add 1 to that. So I'm going to go ahead and say, but this is less than, I hope everybody agrees with this, x to the sixth plus 1. So right now, we have the following inequality. X to the sixth is less than x to the sixth plus 1. Now I'll just take the seventh root of both sides, so I can get x to the 6 over 7 versus the seventh root of x to the sixth plus 1. And you get to that point right there, everybody applauds. They say, great, now I'm going to take the reciprocal of both sides. And here's where the uh-oh happens. When you take the reciprocal of both sides, you get 1 over x to the 6 over 7 is greater than 1 over the seventh root of x to the sixth plus 1, which by the way is greater than 0. But that's not going to help us out because we wanted to use the divergence of the area underneath this curve to force the divergence of the area underneath this curve. However, divergence of a function above says nothing about the convergence or divergence of a function below. So we're sort of stopped here. We stare at this and we just don't know what to do. And we can see the mistake right at the beginning, actually. We know where we want to head. We know that when we flip both sides of this inequality, we'll get this side is greater than that side. I actually want it to be the other way around. So I need to figure out something where that inequality is flipped from the beginning. So how am I going to do that? Well, let's think about x to the sixth plus 1 and compare it to something that's slightly larger than it so that I can make this a different inequality. And you might think, well, can I compare that to x to the seventh? And here's where, if you really want to abuse yourself, you can use that racetrack principle a bunch of times, but I'm not going to do that here. I'm just going to make a very simple claim. I happen to know that for x greater than a certain value, x to the seventh is definitely greater than x to the sixth plus 1. And it doesn't have to start at 1. So this is a hybrid of the previous example and what I had said in the previous example, which is that if the claim doesn't work for, let's say, x equals 1, because it doesn't, right? If you plug 1 in, you get 1. That's not greater than 2. So that's not going to work. However, you can always try a claim like this. 2 raised to the seventh power, you better believe that's greater than 2 to the sixth plus 1. 2 to the sixth is 64 plus 1 is 65. 2 to the seventh is 128. At that point, the seventh power takes over and it becomes drastically larger. In fact, you could take a look at the graph of each of these and you'll see x to the sixth plus 1 ends up being less than x to the seventh at some point. Now, if your teacher really wants you to prove that, it would require repeated uses of the racetrack principle. You would call that function f and that function g, and you would say f at 2 is definitely greater than g at 2. We totally know that, just because if you plug 2 in, you would see that. And then you would say, okay, and by the way, f prime of x is 7x to the sixth, and g prime of x is 6x to the fifth. But then you have to actually compare those two. Now the comparison on these actually is not much of a comparison because we now don't have a vertical shift on either of these functions. And so when you take a look at their graphs, they're actually comparable graphs. X to the fifth, as far as going to the right in quadrant 1 here, x to the fifth times 6 might look something like this, where it goes through 1 comma 6. And then f prime, which is 7 times x to the sixth, not only at x equals 1, even though we're talking about x equals 2, but not only at x equals 1 does 7x to the sixth start higher than 6x to the fifth, but because it's a higher power, it rises faster. So from that point forward, I happen to know f prime is greater than or equal to g prime, but you could do repeated racetrack principle here and go all the way until you get all the derivatives gone. You'll get f double prime of x would be 42x. Actually, I'm going to write it as 7 times 6, x to the 5th, and then f triple prime, right? And you keep doing this. Eventually, ... you'll get down to the 7th derivative being 7 factorial, and g, its 7th derivative, would be 0, actually. And so this, by argument, that way you would get that f prime is definitely greater than g prime because it's moving faster, basically. So that's a little more detail than I think most people would require. I think that it's safe enough to go ahead and take that first derivative and just compare 7x to the 6th versus 6x to the 5th. That's an easy comparison. You know that f prime, 7x to the 6th, is greater than g prime, 6x to the 5th, for all x definitely greater than or equal to 2. So we have two functions. The one on the left starts ahead of the one on the right, and the one on the left is faster, so therefore the one on the left is always greater than the one on the right. Okay, great. So what do you do with that? You take the 7th root of both sides, and then you take the reciprocal. Remember, the 7th root of x to the 7th is just x. Take the reciprocal of both sides, and you get this right here. And we happen to know the area from 2 to infinity, and I said 2 on purpose because my claim that I prove over here was for x greater than or equal to 2. And you would look back to your original integral and you'd say, but wait, I'm going from 1 to infinity. Yeah, I don't care. The area underneath this curve from 1 to 2, that's a finite number. There's no need to worry about that. I could start this integral up at a later date, and the convergence or divergence of that integral will not depend on that finite number from 1 to 2, or the finite area from 1 to 2. Since the area underneath 1 over x from 2 to infinity is divergent, and that's again by the power test for improper integrals, and because 1 over x is less than 1 over the 7th root of x to the 6th plus 1, the integral from 2 to infinity of 1 over the 7th root of x to the 6th plus 1 dx diverges by the integral comparison test. Again, if you're worried about the fact that our original problem started with an integral from 1 to infinity, remember we have a theorem that if you break apart an improper integral into pieces, if any of those pieces diverges, the original improper integral must diverge as well. So because this diverges, so does this. All right, so those are 4 good examples, one building on each other. It's a good reminder of how improper integration works and how you would set up your inequalities. To be honest with you, that 4th case is generally a wicked case. It gets more popular as you get into sequences and series. So hold on to the thought process, but you won't see it a lot with integrals. You'll see it a lot more with series. All right, I hope this video is helpful, and I hope to see you in another video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.